Hello, so today we are going to talk about intermolecular forces and how they influence the properties of the physical properties, especially of substances. So intermolecular forces are the forces in between molecules. Those are the forces that are keeping different molecules together and therefore determining if that substance is a solid or a liquid, or when the intermolecular forces are particularly weak, it may be a gas. And typically intermolecular forces are represented as dotted lines in between molecules. And those are different from intramolecular forces. Those are the covalent bonds inside the molecule and are typically represented with continuous lines. So let's just think about the sequence of the what we have learned in the last couple of months. We started by understanding how to write the electron configuration of atoms, and that allows us to determine how many valence electrons there are. Through valence electrons, we learn how to draw new structures, and applying the Vesper theory, we can then infer the molecular shape. Now, the molecular shape, based on the symmetry or lack of symmetry in the molecule, and based on the difference in electronegativity between the atoms, allows us to figure out if the molecule is polar or not. And what we will learn in this unit is to use this information to determine what type of intermolecular forces are involved in that substance. And as we will see, these determine the physical properties like boiling point, melting point, vapor pressure, the enthalpy of vaporization of other change of state, the viscosity of the substance, and its surface tension. So you don't have to remember the actual values of kilojoules, but this what this slide is trying to convey is that intramolecular forces are generally stronger, therefore they require more energy to be broken, while intermolecular forces are generally weak. So what are the effects of the presence of strong intermolecular forces? If the molecules are tightly connected together, you will see a high boiling point, because it's going to take a higher temperature and a higher kinetic energy for the molecule to be able to get apart from each other. And parallelly, you also will have a high melting point. It will be harder for the molecule to evaporate if they are tightly connected to each other, so the vapor pressure will be lower. And it will take a lot of energy to separate the molecule of the liquid so that they can become a gas. So the delta H of vaporization will be higher, and so the delta H of fusion and the delta H of sublimation. The molecule, the substance will also show a high viscosity. Viscosity is the friction when molecules are moving with respect to each other. So a strong interaction slows down this movement, increasing the viscosity. The surface tension will be higher. We will talk about surface tension in the next unit about solution properties. So we are going now to go go through an inventory of all the different intermolecular forces, starting from the strongest and going to explore them in a decreasing order of strength. The strongest, and they are all intermolecular forces, are basically due to some sort of electrostatic interaction, so attraction between charges. So the stronger electrostatic interaction of all is the one that you have when you have full charges, so the attraction between positive and negative ions. That would be an ionic compound. Now, in an ionic compound, we do not have molecule, so it's really not fitting into talking about intermolecular forces. Second to that, you have the interaction between an ion and a dipole being a molecule that shows polarity. So, for example, the molecule represented in the picture, a molecule of water, interacting with sodium ion in the process of dissolving, let's say, sodium chloride. Number 3 in order of strength, decrease in order of strength, is the dipole-dipole interaction. In this example, we see hydrogen chloride where there is a polar bond. Chlorine is more electronegative than hydrogen. Therefore, the dipole here would be could be represented by an arrow like that, where chlorine represents the negative pole of the molecule and hydrogen the positive pole. And you see that two molecules of hydrogen chloride could interact with each other. The positive side of one molecule would interact with the negative side of the other molecule, and the negative side of the first molecule could interact with the positive side of this molecule. So you can imagine all this interaction happening across several hydrochloric molecules. So these kind of dipole are called permanent because they always exist. They are intrinsically present in the molecule, and there is one special instance of dipole-dipole interaction that's particularly strong, and is called the hydrogen bond. Hydrogen bond happens when you have a polar bond between hydrogen and another element, and the other element can only be oxygen, nitrogen, or fluorine. So for example, here you can see the hydrogen of one molecule of water that is positively charged because it's bonded to the more electronegative oxygen, and it could make an hydrogen bond that's represented by these three red dots with the oxygen of a second molecule of water, and this would make the molecule of water stick together and be liquid. The hydrogen bond can also happen between hydrogen and nitrogen, but can also happen between different molecules. So for example, you can have a hydrogen bond between the hydrogen of ammonia with the oxygen of water, and so forth. So how come there is only nitrogen, oxygen, and fluorine that are able to make this type of bond, hydrogen bond? So for the hydrogen bond to happen, first of all, you need to have a very polar hydrogen non-metal bond, and nitrogen, oxygen, and fluorine are good candidates for this because fluorine is the most electronegative of all, and oxygen and nitrogen that are very close to fluorine in the periodic table, they're just one step away and two steps away, are also very electronegative. So these three elements, they have the necessary high electronegativity to make the bond between them and hydrogen quite polar. But also they are relatively small because they are in the upper part of the periodic table, they are in period 2. And if you remember, fluorine is the smallest of all. And this means that in this interaction, the hydrogen can come very close to nitrogen or oxygen or fluorine, therefore making the bonds more effective. So it's a sweet spot between high electronegativity and a relatively small size. Hydrogen bonds have huge consequences on the physical properties of substances. So in this graph that looks a bit complicated initially, you see the boiling point of a bunch of substances. So each line connects hydrogen compounds of non-metals that belong to the same group. So for example, the red line connects elements, hydrogen compounds of elements that are in the oxygen group, so group 16, and so forth. So for example, the blue line connects the blue line connects hydrogen compounds with halogen, and so forth. So you see that there is obviously a trend. The smaller is the non-metal, the lighter is the non-metal, the lower is the boiling point. And this kind of trend appears very consistently for each group, for each of the 4 groups represented. So we would expect that if we add oxygen to this graph, and that would be water, H2O should be here, and HF should be here, and ammonia should be here. And what happens instead, when we go and measure the boiling point of those 3 compounds, we see behavior that deviates very impressively from that trend, except for methane. Methane does follow the trend as expected. So what is it that makes water having such a high boiling point with respect to hydrogen sulfide? Hydrogen sulfide is a gas and water is a liquid. So there has to be in water intermolecular force that is so strong that is keeping the two molecules of water very tightly connected together. And this is hydrogen bond. So you see this deviation from the expected boiling point for water, so oxygen, hydrofluoric acid, so fluorine, and ammonia, so nitrogen, because those three elements are able, when connected to hydrogen, to make hydrogen bonds. Methane is not enough electronegative respect to hydrogen to make a polar bond, therefore you do not have hydrogen bonds in methane. This shows you some effects of hydrogen bonding. The presence of hydrogen bonding will determine the substance will have high boiling point and a high melting point, and will also produce a high viscosity. So think about, for example, maple syrup is a very viscous liquid because it contains a high percentage of sugar. Sugar has a lot of oxygen and hydrogen bonds that would make a very large number of hydrogen bonding. On this side, of the slide, you can see the alpha helix of protein. So you see a sequence of amino acids all connected through covalent bonds, and there are hydrogen bonds that are stabilizing the structure of the alpha helix. So these hydrogen bonds are very important to determine the 3D shape of proteins. This molecule here is ethylene glycol that's used as antifreeze, and it has two potential sites for hydrogen bonding, here and here. And in fact, you can even have an hydrogen bond that kind of close the molecule in a sort of a circle, so between two different portions of the same molecule, creating a sort of an intramolecular hydrogen bond, so that we can almost represent the ethylene glycol as a pentagonal cyclic structure. So here we see a sequence of hydrocarbon. Hydrocarbon are compounds in which you have only carbon and hydrogen. So you start from methane that has only one carbon, and then we progressively increase the number of carbons until getting paraffin wax, where the number of it's more of a mixture, but on average the number of carbons is around 30-ish. And so what happens is that you go from gas for methane, and then eventually they become liquids, and then eventually they become solid. And so you see an increase in the boiling point and an increase in the melting point. And so carbon-hydrogen bond is considered non-polar. There is in fact a small differences of electronegativity, but it actually has not much consequences. So these molecules are non-polar. There are no dipoles. So if there are no dipoles, what are the forces that are keeping the different molecules together, eventually making it even a solid? So in this type of compounds, of substances, we can have what are called London forces or dispersion forces. So you can imagine the molecule as having a certain amount of electrons used for the covalent bonds inside the molecule, and also maybe in shared pairs. And those electrons are distributed evenly on average because the molecule is non-polar. However, they can randomly modify their distribution, and so it could happen that just by chance every now and then the electrons are mostly on one side of the molecule. This would create a temporary dipole. If a temporary dipole is created, the molecule that's next to it would also be have the induction of a dipole in itself, because this portion of the first molecule will become positive, and this would attract the electrons from the second molecules. And so this way you can imagine that you can determine the presence of an electrostatic interaction between the molecule. So these type of forces are quite weak. They become important only if there are none of the forces we have mentioned so far present. If there is a permanent dipole, if there is a nitrogen bonds that is so strong that dispersion forces becomes irrelevant. But if there is nothing else, then they become important. And they increases with the molar mass, because the larger the molar mass, the larger is the number of electrons in the molecule, the more likely that you have this random redistribution of the electrons. So this property that a molecule that is non-polar could become polarized is called polarizability. Polarizability. It's kind of a mouthful. If a molecule is very polarizable, it means that it's relatively easy to create a temporary dipole. And the main factor is the number of electrons that's correlated to the molar mass. So you can see here you have methane, in which you have bonds between carbon and hydrogen. Those bonds are non-polar, so the molecule is non-polar. Then you have CH4. Carbon fluoride bonds are very polar, but this molecule would be a tetrahedron based on the Vesper theory, and it would be perfectly symmetrical because all atoms are identical. So all those each dipole of each bond will sum up, giving a big zero as a total effect. So that molecule is also non-polar, despite the fact that there are polar bonds inside. And then we have seen similar compounds in which we put different halogen instead of fluorine, chlorine, bromine, and iodine. Now, iodine is the heaviest of all, so the molar mass will have the largest value for Ci4 and the smallest value for methane. So we're comparing molecules that are all non-polar, and they only differ for their molar mass. As the molar masses increases, we go from gas to liquid to solid, and consequently we see an increase of the melting point. And this is due to the fact that Ci4 is more polarizable than CH4 because it has more electrons. In this slide, you can see the boiling point of noble gases, group 18, and halogen, group 17. Noble gases are monatomic and neutral, so they are absolutely non-polar. It's really hard to make helium liquid. If you see the boiling point is 4.2, so it means that to have liquid helium I need to cool down at 4.2 Kelvin, so I'm only 4 degrees away from absolute zero, so it's an extremely low temperature. As the atomic mass increases and I have more and more electron, I see an increase in the boiling point, so it's much easier to liquefy xenon rather than helium. A similar trend is seen in the halogen. The halogen are diatomic molecules. They form these diatomic molecules because they have 7 valence electrons. So to reach the octet, they share the 7th electrons that's unpaired, and they share it with each other, forming a covalent bond that is non-polar because it's in between two identical atoms. So once again, we see that iodine, that has the highest molar mass and has the highest number of electrons, is going to be the one with the highest boiling point. Now let's compare Br2, so this compound here, with ICl. So ICl is an interhalogen, is a compound belong to a class of compounds that are called interhalogens. So those are compounds between two different halogens and nothing else. So in the formula you have only halogens. They are typically binary, like this one. So what happens if you have these compounds as opposed to that? So the bromine-bromine bond is non-polar because it's in between identical atoms, while the bond between iodine and chlorine is polar because electronegativity increases going up, right? So this is the trend for electronegativity. Fluorine is the most electronegative of all in the periodic table, so iodine is less electronegative than chlorine. So here I would have polarization of this bond in the direction of chlorine. So this is a dipole, while this is a neutral molecule. So it's a non-polar molecule. So for a non-polar molecule, I expect only dispersion forces. For a polar molecule, I expect dipole-dipole interaction. And in fact, this reflects into the dramatic difference in the melting point, much higher for ICL, despite the fact that the number of electrons is exactly the same. So dispersion forces would be identical. But when there are other forces like dipole-dipole, dispersion forces become just background noise, and they are not as important anymore. Another factor that may cause difference in the melting point is the molecular shape. So here we have two hydrocarbon, normal pentane and neopentane. So they have the same formula, they are isomers. The only difference is the way the atoms are connected. Normal pentane has a more of a linear shape, so it's kind of extended, while neopentane has more of a globular shape. So really, due to they are non-polar substances, so the only forces, intermolecular forces present for both of them are dispersion forces. So how are dispersion forces influenced by the shape? That's the only thing that is different for these two molecules. So in general, a sphere is the shape that has the smallest surface per unit of volume. So if the two molecules have the same volume, as we can expect because they have the same number of atoms, the surface area of this cylindrical shape is quite larger than the surface area of this spherical shape. That's the reason why spheres are so common in nature, like droplets, planets are spherical, because it's the shape that minimizes the surface area. Or if you want, seals, these are animals that live in a very cold climate. They want to minimize their surface to save as much heat as possible because they are mammals, so they tend to have a kind of a globular face shape. So therefore, having less surface, we expect the dispersion forces to be weaker because they have less room to happen. And in fact, neopentane has a lower boiling point than normal pentane. So let's recap all the intermolecular forces we've seen so far. The strongest are the ion dipole, and then we have dipole-dipole, but in the group of dipole-dipole interaction, we need to remember that hydrogen bonds, that's a special case of dipole-dipole, and those are the strongest. And finally, dispersion, London forces, that becomes relevant only in the absence of the former three. So this is a flowchart that allows you to classify the intermolecular forces. So the first thing that you want to figure out is if there is any ion present. If you have ions interacting with other ions, then you have an ionic bond, and your decision is made based on what you learn about lattice energy. Lattice energy is the amount of energy that it takes to break an ionic bond, and so it's a measure of the strength of the ionic bond, and it's larger if you have more charge on the ions, a larger charge on the ions, and also if you have smaller ions because they can get closer to each other. If you have ions and polar molecules, then you can have ion-dipole forces. Really, the most likely example that you can get in a question, in a test, is ions dissolving, ionic compounds dissolving in water. If there are no ions, then look if the molecule is polar, and you will make your decision based on your knowledge of the Vesper theory, and then polarity of bonds and the shape of the molecule. If you have dipole-dipole, if you have dipoles, then you can have dipole-dipole interaction, in which case check if you can make hydrogen bonds, so if there is nitrogen or oxygen or fluorine bonded with hydrogen. Hydrogen bond would determine very strong intermolecular forces, and therefore high viscosity, high boiling point, and so forth. If you do not have dipoles, then becomes important to look at dispersion forces, and those are correlated with number of electrons, so basically with the molar mass. So when you are asked in a question to rank molecules, and they want to see if you have understood the concept of intermolecular forces, they rarely ask you directly, explicitly, to rank by strength of intermolecular forces. They typically ask you to rank molecules based on the effect, on the consequences of intermolecular forces. So they would ask you to rank molecule by melting point, or by boiling point, or by viscosity, and so forth. So this is an example, right? So in this question, they're asking for each pair of substances, identify the key intermolecular force and predict which one in the pair has the higher boiling point. Now, that's a nice question because they do mention the word intermolecular forces, and that helps you to know what to look for in all the information you have in your brain. But most of the time, intermolecular forces is not mentioned in the question. The question would be just predict which one of which substance in each pair has the higher boiling point, and you may get a little bit confused. And what they're asking you is actually to determine the intermolecular forces. So let's look at the first one. We have magnesium chloride and phosphorus chloride. Now the difference is that magnesium, so you want to look for what characteristic is different between the two compounds. So it's obviously not chlorine. Chlorine is in both. Is the other element. So magnesium is a metal, phosphorus is a non-metal. So the first compound is an ionic compound, the second one is a covalent compound. So which one is going to have the strongest interaction? Even if in your covalent compound you have a polar bond, so that's a polar molecule, and it would be polar because the geometry, if you would look at the Vesper theory, it would not be symmetrical. But magnesium chloride, being ionic, supersede in strength. So that's going to be the one with the higher boiling point. Example number 2, you have molecules that contain polar bonds. So even if it's not that obvious, if it would be my question, I would give you the complete formula where you can see all the bonds. This nitrogen here is bonded to carbon, and this fluorine here is bonded to carbon. So nitrogen carbon bonds is polar, fluorine carbon bonds is polar, but the thing is nitrogen is also bonded to hydrogen, so this is the potential for hydrogen bonds. So hydrogen bonds respect to just plain basic dipole-dipole bonds are going to be stronger. Therefore, in this case is the difference is between the presence or absence of the hydrogen bonds. In the pair showed in C, you have 2 alcohol. This is methanol. This, let me get the laser pointer. This is methanol, and this is ethanol. So this is the alcohol that you have in alcoholic beverages. Methanol is actually toxic. So in this case, you have the possibility of hydrogen bonds in both. So what matters, so those are strong interaction, but they are the same. So the next thing we are going to do is the background dispersion forces that are always there. And because ethanol has a larger number of atoms, has more electrons, is going to be the one with the highest boiling point. In D, we have 2 compounds with the same formula, normal hexane that has 6 atoms of carbons connected linearly, and 2,2-dimethyl butane that has this globular form. But there's also 1, 2, 3, 4, 5, 6 atoms of carbon. So they have exactly the same formula. They are isomer. So in this case, what matters is the shape. A globular shape will reduce the surface interaction because there is less surface area. So normal xn is going to be the one with the higher melting point. This is another example where you have CO2 and water. So for CO2, so they're both covalent compounds, but water has a bent shape, so it's polar, and has the possibility to do polar hydrogen bonds, so very strong interaction, while CO2 has a linear shape. So despite having polar bonds, the molecule as a whole is not polar, so the only forces are dispersion forces. In this last slide, we are comparing methane and CO2, carbon dioxide. Methane is a non-polar molecule because the carbon-hydrogen bonds are not really polar, and then also the molecule is perfectly symmetrical, is a tetrahedron. CO2 does have polar bonds between carbon and oxygen, but because the molecule is linear, the two dipoles cancel out, and so the molecule as a whole is non-polar. So they are both non-polar molecules. The most important intermolecular interaction are dispersion forces. And so what becomes really critical is the molar mass and the number of electrons. That's higher for CO2, and therefore CO2 is going to be the one with the larger boiling point. So that's all for today. The next slide would be about the next lecture will be about solutions and properties of solutions.